In this lecture, we talk about Maxwell's equations. Now, Maxwell's equations unify all electric and magnetic phenomena. So there are four equations, and these four equations taken together will describe all phenomena associated with electricity and magnetism. So the first of these equations is Gauss's law. So this you have seen before. So you have line integral of electric field, then dA vector. This is equal to charge over epsilon naught, which is permittivity of free space. Now the second is Gauss's law of magnetism. Again, line integral of, now you have magnetic field B vector here. This is the magnetic field. Then dA vector, this is equal to 0. The third is Faraday's law. So again, line integral electric field, and then you have small path ds vector. This is equal to minus d phi e by dt. This phi e is the flux. And the fourth is the Ampere-Maxwell law. So again, you have the line integral b vector with dA vector mu naught times I plus id. This is the drift current we described in the previous lecture. Now these four laws which we have just listed above, so these laws describe all electric and magnetic phenomenon. Now if you solve these four equations, you will get the equation for the electromagnetic wave. But this is beyond the scope of our lectures. So we are just going to write down the equation of the electromagnetic wave. So before we describe the electromagnetic wave, first thing to notice is that electromagnetic wave consists of electric field and magnetic fields. So there are two components. One is electric field and another is magnetic field. Now both of these fields are perpendicular to each other. So electric field is perpendicular to magnetic field and to the direction of propagation. So say you're propagating in z-axis. So that means electric field is perpendicular to z-axis, magnetic field is perpendicular to the z-axis, and then electric field and magnetic field are perpendicular to each other. So let us see what are the equations. So there are two equations which describe the electromagnetic wave. So first concerns the electric field. So this is E is equal to Em. This Em is the maximum value, sine of kz minus omega t. Now this k is a constant. This k is equal to 2 pi by lambda, where lambda is the wavelength. Z is the direction of propagation. Omega is the angular frequency, which is 2 pi f. So notice that lambda times f is 3 into 10 to the power of 8 meters per second, that is c. T is time and z, as I said before, is the direction of propagation. So let us see this more visually. So say this is the electric field E. So this is the maximum value. So you will say the direction of electric field is like this because this is where the maximum value occurs. The direction of propagation is z-axis. So this is the direction of propagation. So you see electric field is perpendicular to the direction of propagation. Now wavelength is from maximum value to maximum value. So this part is called lambda. And since you know c is always constant, so you know that lambda times f is constant. So now you can find even the frequency of the wave. So similarly you have the magnetic field. So this is the magnetic field. Again you have the Bm as the maximum value. Notice that the wavelength is the same here, lambda, and now we want to put this electric field perpendicular to the magnetic field. Again, this magnetic field is perpendicular to the direction of propagation z. So this is the magnetic field, and this is perpendicular to the direction of propagation z. So in the figure now, we are going to put both electric field and magnetic field together. So again, we have drawn electric field here in red, magnetic field is in blue. So we have put them perpendicular to each other. So the red part and the blue part are perpendicular to each other. You can see they are both sinusoidal, and this direction of propagation we will call the z-axis.